Representation Theory of Finite Groups, Lecture 23, the Hooke Formula. Let us start with some motivation and recap. Let n be a positive integer, so we consider the symmetric group Sn and the category of all finite-dimensional Sn modules. For a partition lambda of n, we have the corresponding Specht Sn module as lambda. So we know that these modules S lambda exhaust all simple Sn modules. Further, we have the set Syt lambda of all standard Young tableaus of shape lambda. And we have also seen that this set indexes a natural basis in the Specht module. In particular, the dimension of the Specht module equals the cardinality of this set. The main aim for today is to give a combinatorial formula for the computation of the cardinality of the set of standard Young tableaus of shape lambda. So the main notion behind the formula is the notion of a Hooke. So let lambda be a partition of n, which we view as a Young diagram. A box V in lambda will be usually denoted as ij, which means that it is in the i's column from the left in lambda and in j's row from the top. Definition: if we have a box V in a partition lambda, then the Hooke of V is the collection of all boxes in lambda which are exactly to the right of V or exactly below V, including the box V itself. So here is an example. Consider the partition lambda, which is 6, 4, 4, 3, 1. So this is a partition of 17. And consider the box V in this partition with coordinates 3, 2. So here is a picture. So we have this box in the third column from the left and in the second row from the top. So the Hooke of this box consists of all boxes which are marked by bullets in the picture. So these are all boxes to the right of our original box and all boxes below it. So this is the Hooke. The number of boxes in the Hooke of V is called the length of the Hooke and is denoted by h sub lambda of V. So in our particular example, which we have here, the length of the Hooke for the box 3, 2 equals 4, because there are exactly 4 boxes in this Hooke. So now we can formulate the main result for today's lecture. So we will denote the fact that V is a box of lambda as follows. So V belongs to lambda. So this will mean that V is a box of lambda. Theorem, which is usually called the Hooke formula. For a partition lambda of n, the cardinality of the set of standard Young tableaus of shape lambda equals the following expression: n factorial divided by the product over all boxes V in lambda, and then the factor corresponding to V is the length of the Hooke of V in lambda. So this theorem was originally proved in the paper The Hooke Graphs of the Symmetric Groups by Frame, Robinson, and Thrall in 1954. However, today we will present a beautiful elementary proof of this formula, which is fairly recent. It's from 2008. It is due to Jason Bundlow, and it is taken from his paper An Elementary Proof of the Hooke Formula. So let us first, before we go to the proof of the theorem, let us first look at some examples to see that it works. Consider the partition n of n. So this is just one row partition, and in this picture, in each box, we write the lengths of the Hooke corresponding to this box. All Hookes are just rows, so for this box, we have n boxes to the right, so the length is n. Here we have n minus 1, and so on. So therefore, the Hooke formula reads as follows. The cardinality of the set of standard Young tableaus corresponding to the partition n equals n factorial divided by the product n minus 1, n minus 2, and so on, which is also n factorial, and this gives us 1. And we know that there is exactly one standard Young tableau of this shape. The transposed example, if lambda is a partition 1, 1, 1, 1, and so on of n, then the hook lengths of the boxes in lambda are as follows. So the top box has hook length n because the hook is just the column, and then the next box has hook length n minus 1, and so on. Therefore, the hook formula again gives us n factorial divided by n factorial, which is 1. So there is exactly one standard Young tableau of shape 1, 1, 1, 1, and so on. The next example is the partition n minus 1, 1. So here are the hook lengths for all boxes. So the corner, the top left corner box has hook length n because its hook is the whole partition. But then the box next to it on the right has hook length n minus 2 because there are only n minus 2 boxes to the right of it and nothing below. And then we have n minus 3 and so on. And the only box in line 2 has hook length 1. Therefore, the hook formula for this partition gives us n factorial divided by n times n minus 2 factorial, n times 1. And the outcome is n minus 1, which is exactly the number of standard Young tableaus of shape n minus 1, 1, as we have already seen. And here is an example just to show that it is very easy to compute the number of standard Young tableaus using the hook formula. Consider the partition 4, 3, 2, 1 of 10. Then here are the hook lengths. So the removable boxes, of course, have hook length 1. Then the boxes above them have hook length 3. So this box has 1 to the right and 1 below. So the next inverse diagonal has hook length 5. 1, 2, 3, 4, 5. And the top left corner has hook length 7. 1, 2, 3, 4, 5, 6, 7. Therefore, the hook formula gives us that the number of standard Young tableaus of shape 4, 3, 2, 1 is equal to 10 factorial divided by 7 times 5 squared times 3 cubed. And then it's easy to compute that the outcome is 3 times 2 to the power 8, which is 768. Okay, let us now prove the hook formula. The proof will be quite long, and before we go into details of this long proof, we have to do some preparation. So we will prove the statement by induction on n, and we will use the branching rule, which we have already established. Recall that the notation mu arrow lambda means that mu is obtained from lambda by removing a removable box. So we will proceed by induction on n, and the case n is equal to 1 is obvious. So the main point of the induction step is that induction step is equivalent to the following formula, that the sum over all mu such that mu arrow lambda, and then the expression which we sum is the product over all v in lambda, the hook lengths in lambda of v, divided by the product of all w in mu, the hook lengths in mu of w. So this expression is supposed to be equal to n. So the claim of the proposition is that the induction step reduces exactly to proving this equality. And this is this equality which we will prove in kind of the main part of today's lecture. So let us prove the proposition. Let us really establish that the induction step for the hook formula can be reinterpreted as this equality. So recall our branching rule. So we know that if we take the Specht module as lambda and restrict it from Sn to Sn minus 1, this decomposes into a direct sum of S mu, where mu arrow lambda. In particular, This means that the cardinality of the set of standard Young tableaus of shape lambda is equal to the sum over all mu such that mu arrow lambda, the cardinality of the set of standard Young tableaus of shape mu. So now if we plug in the Hooke formula into this equality, so we get on the left the expression of the Hooke formula for SYT lambda, and on the right the sum over all mu arrow lambda, and then the expression of the Hooke formula for SYT mu. So this we know by the branching rule. By the inductive assumption, we may assume that the right-hand side is correct. So the Hooke formula for the left-hand side really is equivalent to establishing this equality. What we can do now, we can multiply with the denominator of the left-hand side and divide by the numerator of the right-hand side. So n factorial divided by n minus 1 factorial gives us n. And when we multiply with the denominator of the left-hand side, and in this way move it to the right, we will get exactly the expression on the left-hand side of our proposition. So this completes the proof of our proposition. So the induction step for the Hooke formula is equivalent to proving this expression, and this is our aim for the rest of this lecture. So our strategy will be as follows. So we will split the proof in 3 steps. First of all, we will introduce certain numbers, xi and yi, where I is an integer between 0 and m. So in step 1, we will prove that our expression on the left-hand side of the induction step is equal to minus the sum over all I from 1 to m of the following fractions. The numerator is a product over all j from 0 to m, xi minus yj, and the denominator is a product over all j from 1 to m, j is different from I, xi minus xj. On step 2, we will show that this new expression is equal to minus 1/2 the sum over all I from 0 to m, xi square minus yi square. And finally, in the last step, we will show that this expression is equal to n. And this will complete the proof of the Hooke formula. So let us go on with this proof, and let us start with introducing our numbers m, xi, and yi. So we start with definitions. So we set m to be the number of removable nodes in our partition lambda. Next, for a box I, j, we define the content of this box as I minus j. Now we define the boxes capital Xi and capital Yi for I from 0 to m, as exemplified here on this picture, in which case m is equal to 3. So we have a partition lambda here with 3 removable boxes. So we denote by x0 this box, which is slightly outside the partition, next to its top left corner. And then x1, x2, x3 are exactly the removable boxes of lambda. And we also define y0 as this box, and then y1, y2, and so on as the boxes which are to the northwest from the inner corners of lambda. And then y3 is here. So this will be ym in general. Assume that the coordinate of the box xi is beta I, alpha I, and then we have that the coordinate of yi is exactly beta I, alpha I plus 1. So yi is in the same column as xi and is in the same row as xi plus 1. So here we use the cyclic notations that alpha m plus 1 is equal to alpha 0, which is 0. So this is the coordinate of the x0 box. x0 is in the zeros row and in the zeros column. So now we define the small xi as the content of the box capital Xi. Due to our notation for coordinates, small xi is equal to beta I minus alpha I. And similarly, we define the small yi as the content of the box capital Yi, which is then beta I minus alpha I plus 1. So here are two observations. Observation number one, the sum of all small xi's over all I from 0 to m is by definition the sum over all I from 0 to m of beta I minus alpha I. But this is then also equal to the sum over all I from 0 to m of all yi's. So yi is beta I minus alpha I plus 1, but when we sum over all i's, we can then change it to this. So the sum of all small xi's is equal to the sum of all small yi's. The next definition. For a box V, define the two boxes E of V and S of V as follows. We consider the hook of V, and the box E of V is the east end of the top row of this hook. And then the box S of V is the south end of the leftmost column of this hook. So if V is here, then E of V is here and S of V is here. And then observation number two, the hook length of V in lambda is equal to the content of the box E of V minus content of the box S of V plus 1. So this is true because if we will walk along the hook from the box S of V to the box E of V, then on each step the content increases by 1, directly from the definition of the content. And therefore, the number of steps we do is exactly the length of the hook minus 1. So we have to add plus 1 to this expression to get the length of the whole hook. With these two observations at hand, let us now proceed with computations. So the main point is that we have to analyze the expression, the sum over all mu arrow lambda. In the numerator, we have the product of hook lengths of all boxes in lambda divided by the product of the hook lengths for all boxes in mu. And the main point is that there will be a huge cancellation in this product. So recall that we have defined the capital Xi's for I from 1 to m as exactly the removable nodes of lambda. So the summands of this expression are indexed by the xi's. So this is actually a sum over all I from 1 to m, and then we take the corresponding mu, which is obtained from lambda, by removing the removable node xi. So here's what happens if we remove xi. So in this particular example, we look at this picture of the partition where we have 3 removable boxes, and we remove the box x2. So here I is equal to 2. So we have this box x2, which we removed. There is a row in which this box lies, and it also lies in a certain column. If we take a box which is neither in the row of x2 or xi and neither in its column, then for that particular box, the hook length in lambda and in mu is the same. So for any box outside of this row and this column, the corresponding factor in the numerator and in the denominator just cancels. Each box outside this kind of inversed hook for x2 cancels in the numerator and the denominator. But there is even more. So the TL boxes for lambda, so there is a hook here in lambda for the TL box, it has exactly the same length as the hook for the violet box in mu. So we have these pairs of violet and teal boxes, and the violet box is exactly to the left of a teal box. So when we remove x2, then the length of the hook for the violet box in mu equals the length of the hook for the teal box in lambda. So each teal box in the numerator cancels with the corresponding violet box in the denominator. So the main question is what remains? So what remains, the only boxes which do not cancel in any obvious way in the numerator and the denominator are the magenta boxes for the numerator and the cyan boxes for the denominator, as given in this picture. So in the numerator, we have the magenta boxes. There are m plus 1 such boxes. And in the denominator, we have the cyan box. There are m minus 1 such boxes. And we number these boxes in the following way. So we start magenta numbering from the left. So this is L0, L1, and so on, up to Lm. And we similarly number the cyan boxes from the left. This is M1 and so on, MM. So we see that these boxes, they correspond to inner corners of our partition. But we can immediately write down the coordinates. The box Lj, where j is smaller than I, so this is a case when Lj is in the row of xi, which we removed. So the box Lj has coordinates beta j plus 1, comma, alpha I. So if j is greater than or equal to I, then the box Lj lies in the same column with xi and has coordinates beta I, comma, alpha j plus 1 plus 1. Similarly, if j is smaller than I, the box Mj has coordinates beta j, alpha I, and if j is greater than I, then the box Mj, it belongs to the column of xi, so it has coordinates beta I, alpha j. So let us now compute the hooks for all boxes which do not cancel in our fractions. In the numerator, we have the following. If j is less than I, then the east end of Lj is equal to xi, and the south end of Lj is the box which is immediately to the right of the yj. So here is the picture. Lj has xi as the east end, and its south end is next to the right of yj. So Lj has xi as the east end, and its south end is next to the right of yj. So therefore, the hook length for Lj, if j is smaller than I, equals the content of xi minus the content of yj plus 1, 0, and then plus 1. This is exactly our second observation. Now, minus 1 here and plus 1 here cancel each other, and we get exactly xi minus yj. For j greater than or equal to I, the east end of Lj is the box which is immediately below of yj, and the south end of Lj is xi. Here is in the picture. The east end of Lj is the box which is below yj, so the east end of Lj is here. This is a box below yj, and the south end of Lj is xi. Therefore, the hook length of such Lj is the content of yj plus 0, 1 minus the content of xi plus 1. Again, the content of 0, 1 is minus 1, so this minus 1 cancels this plus 1, and we get yj minus xi. Now about the denominator. If j is smaller than I, then the east end of mj is the box which is next to the left of xi, and the south end of mj is exactly xj. So now we are talking about the denominator, so xi is removed. So the east end of mj is the box which is next to the left of xi, and the south end of mj is exactly xj. Therefore, the hook length for such mj is the content of xi minus 1, 0 minus the content of xj plus 1. So here we have the contribution of minus 1, it cancels this contribution of plus 1, and we get xi minus xj. Finally, for j greater than I, the east end of mj is xj, the south end of mj is the box which is immediately above xi. So here is the picture. This is our mj. The east end is xj, and the south end is the box which is immediately above xi because xi is now removed. So therefore, the content of such mj is the content of xj minus the content of xi minus 0, 1. Again, here we have a contribution of minus 1, which cancels this contribution of 1, and we get xj minus xi. Now we can collect all this together. So the expression which we want, the sum over all mu arrow lambda, in the numerator, the product of the hook lengths of all boxes in lambda, divided by the product of the hook lengths of all boxes in mu, is equal to the sum over all I from 1 to m. So this simply indices all mu, which are obtained from lambda by removing a removable node. This is just indices them by our removable nodes x1, x2, and so on. And then for the removable node xi, we have the product of the hook lengths of the magenta boxes in the numerator and the product of the hook lengths of the cyan boxes in the denominator. And we just computed them. So in the numerator, we have the product for over all j from 0 to I minus 1, xi minus yj, times the product over all j from I to m, yj minus xi. And in the denominator, we have the product over all j from 1 to I minus 1, xi minus xj, and then the product over all j from I plus 1 to m, xj minus xi. So we see that the difference between the factors here in the numerator and in the denominator is just the multiplication by sign. So we multiply all factors here by minus 1 and all factors here by minus 1. So the green part changes to minus 1 to the power the number of factors times the product now of xi minus yj. And similarly here we will have one factor less, because j here starts from I plus 1 and here from I. And in the denominator, we will also have now a product of xi minus xj. And now we can collect these products into the same product, both in the numerator and in the denominator. And the factor of signs will just give us one minus sign in front of the whole thing. And we get exactly the expression as provided by the first step of our strategy. So we get minus the sum over all I from 1 to m, and then the summand is the quotient of the product j from 0 to m, xi minus yj, divided by the product j from 1 to m, j is not equal to I, xi minus xj. So this completes the proof of step 1. In step 2, we will have to analyze this new expression in a different way. In order to prove step 2, we consider the following polynomial p of t, which is defined in the following way. We take our expression, so this is what we are analyzing, and then we multiply it, so each summand in this expression is multiplied by the product j from 1 to m, j is not equal to I, t minus xj. So the whole thing is by definition a polynomial in t. What is clear is that the value of this polynomial at xk, so if you plug in xk here instead of t, we will have many zeros except for the summand where I is equal to k, and for that summand this expression will cancel this expression, so we get only the numerator. So we will get exactly minus product of j from 0 to m, xk minus yj. And this is true for any k between 1 and n. Also, directly from the definition, the degree of this polynomial is at most m minus 1, because we can multiply t with itself at most m minus 1 times. And the coefficient at t to the power n minus 1 in this polynomial is exactly the expression which we are trying to understand. This is exactly the expression which we got at the end of step 1. So now we want to compute p of t in a slightly different way. For this, we consider a different polynomial, q of t, which is defined as a product over all j from 0 to m, t minus yj. Again, for any k between 1 and m, the value of q at xk is the product over all j from 0 to m, xk minus yj. The degree of q is equal to m plus 1, this is obvious from the definition, and the leading coefficient, so the coefficient of t to the power m plus 1 in q is obviously 1. Consequently, if we add up p and q, then so the value of p at xk was minus this, so here we have the minus sign, and the value of q is with a plus sign, but then the same expression. So p plus q at xk is equal to 0 for any k between 1 and m. The degree of p plus q is obviously m plus 1, because p has much smaller degree, it has degree at most m minus 1. And the leading coefficient of p plus q is 1. In other words, p plus q must be the polynomial, the product over all k from 1 to m, t minus xk, times t minus a, for some number a which we so far don't know. So this is a polynomial of degree m plus 1, it should have exactly m plus 1 roots. We know m of them, these are xk's, and we denote the last root by a. This allows us to compute the polynomial p as a difference between p plus q and q. So p of t is t minus a times the product over all k from 1 to m, t minus xk, minus the product over all j from 0 to m, t minus yj. So let us write down this polynomial explicitly. So the term t to the power m plus 1, from the left summand and the right summand, these two terms obviously cancel. Then we have t to the power m with the following coefficient. So from the first summand we have minus a, and then plus minus x1, minus x2, and so on. So minus the sum over all xk's. Similarly, from the second summand we will get the sum over all yj's. So this is a coefficient at t to the power m. Next, let us look at the coefficient at t to the power m minus 1. We need to take the product between the roots from the first summand and from the second summand. So the product from the first summand gives us a times the sum of all xk's, and also plus the sum of all xk times xj, where k is smaller than j. And similarly here we will get minus the sum over all k smaller than j, yk times yj. And then we will have lower order terms, which we are not interested in. We know that the degree of p is at most m minus 1. This means that the coefficient at t to the power m must be 0. So a is equal to the sum of all xk's, k from 1 to m, minus the sum over all yj's, j from 0 to m. But we also know that x0 is 0, so we can start from 0 here. And by observation 1, the sum of all xi's is equal to the sum of all yj's. So a is equal to 0. Great. But if a is equal to 0, then this summand disappears, and it means that the coefficient at t to the power m minus 1 in p of t is just the sum of these two summands. And again, since x0 is 0, we can start from 0 here. So this means that the coefficient at t to the power m minus 1 in p of t is the sum over all k greater than or equal to 0, less than j, and this is smaller than or equal to m, xk xj minus yk yj. And this, in turn, equals 1/2 of the following expression, the sum of all xi square minus the sum of all yi square minus the sum over all I of xi square minus yi square. So if we open these two brackets, we will get the sum of squares of all xi's, the sum of squares of all yi's, and then they are double products. And when we take 1/2, we will get exactly this expression. from observation 1, it should be observation 1, not observation 2, we know that the sum of all xi's is equal to the sum of all yi's. So the sum of all xi's square is equal to the sum of all yi's square. So the first two summands just cancel each other. Therefore, we get that this expression is equal to minus 1/2 the sum over all I from 0 to m, xi squared minus yi squared. And this completes step 2. Let us now go to the final computation of step 3. So we need to show that minus 1/2 of the sum of xi squared minus yi squared is equal to n. Recall that xi is beta I minus alpha I, and yi is beta I minus alpha I plus 1. So let us do the computation here. So we start with this expression, plug in the values of xi and yi, so we get this expression. And then here, when we open the square brackets, we will have that beta I squares, they all cancel. And the only non-canceling alphas will be alpha 0 squared and alpha m plus 1 squared. But alpha 0 is equal to alpha m plus 1, so they will also cancel each other. And that what remains is minus 1/2 of the sum over all I from 0 to m. From here we will have minus 2 times beta I alpha I, and from here we will have plus 2 beta I times alpha I plus 1. And this gives us the sum over all I from 1 to m, beta I times alpha I minus alpha I plus 1. This is because beta 0 is 0. So this is the expression, and we need to show that this expression is equal to n. And then we just need to look at the picture. So this expression, in fact, computes the area of our partition lambda, and this area is equal to n because lambda consists of n boxes, 1 times 1 each. And this is illustrated by this picture. So beta 1 is by definition the length of this side. And alpha 1 minus alpha 2 is the length of this side for this rectangle inside lambda. So beta 1 times alpha 1 minus alpha 2 is the area of this rectangle. Next we have beta 2. This is the side of this rectangle. And then we have alpha 2 minus alpha 3. This is the length of this side of this rectangle. So beta 2 times alpha 2 minus alpha 3 will give us the area of this rectangle. And so on. When we add up the areas of all these rectangles, we will get exactly the area of lambda, which is equal to n. And this completes both step 3 and the whole proof of the hook formula. So here are some problems and questions. Question 1. Compute the number of standard Young tableaus of shape 4, 3, 2, 2, 1, 1. Question 2. Compute dimensions of all Specht modules for S7. Question 3. Determine all lambda for all n such that the dimension of S lambda is equal to 2. Question 4. Check all the details in the cancellation part of step 1. And finally, question 5. Assume that n is prime and lambda is a partition of n such that lambda 2 is greater than 1. Show that n divides the dimension of S lambda. Thank you very much, and see you next time.